Check, check. I'll give it a minute or two to see who else shows up. Okay, well, I'm going to go ahead and get started. So do we have any questions before I start up today? Hope everybody had a good break. Can everybody hear me okay? Good, thank you, Nick. Okay, so I was hoping that I didn't have an audio problem or anything. Okay, so what we're going to start off with today is let's create a little list class here that we can use kind of as an example to kind of roll along here. I'm going to call it my int linked list. And inside of here, he's going to have a class node, which is going to take a val value int, something kind of like that. And let's also give it a var next, and it'll be a node nullable, defaulting to null. And let's add in a little fun insert here. And we'll say value int. And we need a private var head. And it's a nullable node. We'll start at a null. And then we can say head equals node value head. So we'll do something. This is just going to be a really simple linked list where we're always just inserting in the front of the list. So just to make this kind of go through fast. I'm not too worried about the data structure itself as things we can do with it and how we can interact with it. Now let's make this thing so that we can figure out how many items are in it as well. So we'll have a var size colon int equals 0 with a private setter. And then we can say size plus plus there. That'll be pretty good. So they'll keep track of how many items we have. And then let's give a way to get items out of the list. So we'll have an operator fun get index int, and he's going to return an int. And inside there, we will say, let's see, how do I want to do this? We will say var temp equals head, and then repeat index temp equals temp.head, temp.next, something kind of like that. Now this isn't a, we're not checking for out of bounds or anything. If we just run off the end of the list, we run off the end of the list and it's null, so not a big deal. So actually this should be nullable to return there. And then we can return temp.value, something kind of like that. So nice, simple little list structure here. And we can use this pretty easily. We can say, I'll just call it list1 equals my int linked list. And then we'll say list1.add, and we'll throw some numbers in here. Let's go 5, whoops, insert, not add. 4, 3, 2, 1. And because they go in backwards, we should end up seeing those items as we walk through them. And let's just make sure that we can walk through this. We'll do a, let's see, 0 to list1.size. Actually, let's make that be an until. So that'll be exclusive on the top side. Dot repeat. Oh, let's actually do a repeat outside of there. Do this right, Scott. There we go. Oh, wait a minute. Actually, I wanted to just do that as a for each. Okay, so now this is going to let us walk through the list and actually print stuff out. So let's actually print out println list1 sub it. Let's just try that just to see if this actually works for us. And there we go, 1, 2, 3, 4, 5. So it's printing things out. There's reversed from the order we insert. We expect that. This allows us to actually work with this little list. So decent little data structure here. Let's say that we want to do the same thing for strings. I'm going to come in here and say my string linked list. And then we're going to have to replace the ints with strings for the values there. Something kind of like that. And then we should be able to do something similar here with list2 for a string linked list. And we're going to insert E, D, C, B, A, something kind of like that. And whoops, what did I? Might help if I actually change the number of the list there for the variable. There, now he's happy. And so now I can say inside here, list2 to that, and we should see both of those lists print their stuff. There we go. We got our A, B, C, D, E, and we got our 1, 2, 3, 4, 5. So that's all working just fine. Simple data structures here. But when we take a look at this, we've got a lot of redundancy in these two classes. Everything is exactly the same, except for the type of these values. And it'd be really nice if we could use the exact same code and just change up that type. And this is where generics come in. What we can do with this is we can actually make that type be a parameter for when we end up creating this class. So let me take everything that I got inside here, and I'll paste it in there. And let's get rid of one of these. What I'd like to do is everywhere that I have that int that represents the type of this list, I'd like to use a variable for it. So what I'm going to do is after linked list up here, I'm going to put in the word type inside brackets. Note that you can use any name you want up here. Typically, you'll do it all uppercase. Most of the time, you're going to see people use a single letter for this. Depending on what you're doing, there's times when I really like to use a very specific full spelled out name rather than just TUV, which is pretty common for people to use. If it's just a single type that's going to be your generic type, a T will be fine. I'm just going to spell it out just to show you that you can. A lot of times people don't even realize that you can actually use a longer name. And later on, there's actually an example I'll show you where it actually is more readable to see different names there. So what we're going to do is we're going to take that type, and everywhere that we have int here that we're using for the value, I'm just going to put in type. And we'll come down here. This guy's going to return type. And I think that is it. So now we have the exact same code that we can run for any type of list here. And what is he not happy about here? Now the problem here is that this class here, because he's not marked as an inner class, he doesn't have any type of access to the data in the containing class. He's completely standalone. So he doesn't have any idea what this type means. Now there's two ways we can handle this. We could make this an inner class, and then he'll have accessibility to those. But at the same time, that means that every node is going to have an implicit pointer to the list that contains it. And in this case, we don't really need that. We don't need that extra data. What we do instead is we say that node is parameterized by type as well. And then when we create nodes down here, we say the type of node that we want to use is one that holds on to the same type of items the overall list holds on to. And boom, now everything there looks just fantastic. So let's see what happens when we actually want to use this. We'll come down here. I'm going to change the name of this to just my linked list instead of my int linked list. And let's make this be a list of integers. Boom. And notice how that compiles just perfectly fine. We've replaced the actual type with int. Boom, all those work. And we can do the same thing here. Change this to be string. And boom, all those work just as well. And if I run this, I should see the same result that I did before. There we go, 1, 2, 3, 4, 5, A, B, C, D, E. And this was kind of the initial impetus to generics. And I'm not sure if C++ was really the first language to go down this route. I think other languages probably did, but I just don't happen to know off the top of my head. The first time I used it was in C++, and in C++, it was a very simple templating language. And they used to call them templates to start with. And actually, I think they still do call them templates, but it was basically a textual substitution that you were doing. And what would happen is when you created the instance of this guy, it would just take whatever you passed in there and actually replace the word type with that type that you're creating there. So it really was just textual substitution. It's come quite a bit farther than that, both in C++ and in Java and in Kotlin, so that now it's actually a first-class construct in the language rather than basically a preprocessor directive. So what this is going to do is actually instantiate this guy with that type, and we can use it. We can use it for any type we want now. So if I came in here and let's say that I created a abstract class mammal, and we'll create a open class cat. We'll give the cat a name, who's going to be a mammal. And let's make a class tabby, who's going to be a cat. Something kind of like that. And maybe we'll also create, oops, lost my focus. Maybe we'll also create a dog here, who's going to be a mammal. And he doesn't need to be open, neither does the tabby. But I'll just go ahead and make him open just for the heck of it. And so we could actually create lists using these guys as well. So I could come down here, and let's say that I want to create a list 3. It's going to hold mammals. And then inside of here, I'm going to insert a dog, Fido. Uh-oh, something doesn't seem right here. A cat, let's say Fluffy. There we go, that's much better. Didn't even notice that. I'm like, why is this giving me an error? Okay, so, and a tabby, which is going to be named Thunderbean, and another dog that we'll name Rex, and maybe another cat we'll call puffball. Okay, and I actually did have a cat named Thunderbean. I don't want to get into the story behind that. It's a long story, but Thunderbean, I think, is the best name in the world for a cat. So we now have this list. Let's do that, and let's just see. Oh, you know what? That just got lucky that worked there when I had the list one down that one. Let's try this and see if it'll print out those as well. And I don't have any toStrings in those ones. So let's actually, can we do a .name? No, we can't do a .name because mammal doesn't have name. Let's actually go to mammal and say abstract val name : string. And then I should be able to, whoops. I should be able to just print the name rather than defining those toStrings all over the place. And we'll run that. And that's much better. So we get our 1, 2, 3, 4, 5, our A, B, C, D, E, and then our cats. So any questions so far? So this is a really simple example of making a class be generic so that we have a type we can replace. It's a very simple operation at this point. Any questions so far? Okay, so let's see what we can do with some of these things. Let's say that we have this kind of a list, and let's see, which example did I want to show first on this one? Let's say that we want to get a little bit more interesting in how we keep track of things here, so that we have a list of things that we can access, kind of like we're doing here, but maybe we also want to be able to sort them. Let's take a look at some concepts that we want to implement here. So we're going to start off by saying that, where did I put that? Let's say in order to be able to sort things, the things themselves, we want to be comparable. So I'm going to define an interface here called comparable. And comparable is going to have to depend on the type of the thing that you're comparing. So you can actually get to some fields and do something interesting with it. So I'm going to say type on him. And he's going to have a single method called compare to. And we're going to say some other guy of the same type. And that's going to return an int. If the int is less than 0, that means that they're already in the right order. That means like the object that I'm comparing is before this other object. If it's greater than 0, then you should swap the order. If it's equal to 0, that means that they both should have equal content. One thing that's kind of neat about this is if I make this an operator fun in Kotlin, this can now be used in a less than, a greater than, not equal, and equal operators. Sometimes that's useful. A lot of times it doesn't really make a lot of sense, but this could allow you to kind of more natively order things if you wanted to. So we're going to say that something is comparable for some type if we actually have this compare to method for that type. Now notice that this type is there just for use as that parameter. This means if I had an object that I wanted to make comparable, like if I had a class, I don't know, card, like a playing card, what I have to do here is say that he's comparable and he requires a type to be passed in. So we're going to say, what is the other thing we want to compare it to? Well, I'm going to pass in card here. And sometimes this confuses people when they say, see, something extends something else with the same name. In this particular case, we're just saying, what is the other thing we're comparing it to? Now, sometimes this interface actually needs to know what type this first thing is so that it can actually get more information out of it. And you'd have the same kind of thing where you'd have the interface taking the name of the thing that you're extending. All it's doing is saying, give this guy access to this type. So we'll know that the overall object I'm implementing is this type here. So let's implement this member here. So we fulfill that. And then we would have some kind of implementation there to say if this one card is less than another card. So if you were like playing blackjack or poker or something, you could have this function telling you which cards are worth more than others. So I guess it'd be more for poker. Blackjack, it's like you're talking about a count. So in here, we might have a card keep track of a suit and a rank. And based on the suit and the rank, this compare to function would return -1, 0, or 1, perhaps, just to say what order they should be appearing in. Now, we're not going to actually implement that. I just wanted to kind of show you what it would look like so you can see this thing here. And keep in mind, sometimes the specification will be a little bit more complex than this. We might see some later on. But what we're really looking at is comparable needs to know the type so we know what we're comparing to. Okay, I'm just going to comment him out because we really don't care about that for the moment. So we got our comparable guy. Let's say that we also want to have some interface that tells us a data structure that we can get things via random access. So if I say interface random access, he's going to have some type associated with him. So he's going to say the elements of the item. Let's actually call that item type. Why not? So the items that we're going to be working with and getting randomly are going to be represented by this item type, generic type. So inside here, we're going to need 3 functions or 3 members. We're going to have a size, which is an int. So we just know how many items are in that guy. And then we're going to need a way to get and set them. So I can have an operator fun get taking an index, which is an int, and he's going to return something of item type. And if it doesn't exist, let's go ahead and make that nullable to say that, hey, the thing doesn't exist. And then we can do something similar with a set, except what he's going to do is take an item in as his parameter. So this specification here tells us we have some object that we can get the size of, we can get items, we can set items. That's really what we need to know that something is a random access object. So that's kind of interesting there. And we could implement this random access guy on our list. So if I came and got our list class here, grab it from that package. Let's say we throw him in there. We could add in random access, passing in the item type. And let's go ahead and change this to be item type here. Something kind of like that. And I'm going to do the same thing here for this guy. Item type, there we go. And right now we only have this get function. We haven't implemented the set. And I'm going to throw him in there, but I will say left as exercise for interested reader. I'm not interested in actually fleshing out the actual how stuff is done inside here so much as what is done. I just want to know that I can set things, I can get things. And we're going to notice that this get now needs an override because he's overriding an item in that interface. Any questions so far? And same with size, we need an override on him. So we've now defined a class that's going to implement random access. So that's fantastic. Now what I'm going to do is I'm just going to kind of wave my hands at that for the moment. I'm not going to care about an actual implementation of it. I'm just going to be specifying some stuff in terms of these interfaces so we can actually do some things with them. So let's say that maybe we want to implement a sort function. And the sort function is going to have to run through all the items in this list, move them around as need be, and so on. So let's take a look at what that might look like in terms of these interfaces. We're going to have the items themselves be comparable, and we're going to have the data structure that's holding them be a random access guy. So let's take a look at how this might look like. Let's, first of all, without specifying any generic stuff, let's write this as though we have a bunch of ints inside here. So I'm going to start off with a fun, and I'm going to say we have a random access int. We'll do something kind of like that. And int we know is comparable, so we don't have to worry about that interface for the moment. And I'm going to call this sort. So I'm now defining an extension function on random access for integers, which allows us to sort some random access thing with integers in it. So let's think of what the code is going to look like inside there. I'm just going to write a super brain dead bubble sort here. Don't ever do this in real life, but just to show you what a sort is, I'm going to implement a bubble sort. So let's do a 0 until size. So we're going to get the size from that receiver, the random access. And I'm going to say for each, and we'll call that, whoops, wrong for each. I'm going to call that I. And then we'll do an I plus 1 until size for each. I'd do a quick sort, but I don't want to spend the time writing it out and then explaining it because it's a lot of fun. So we have our really just brain dead bubble sort loops here. The order of the big O notation on this would be n squared for the order of complexity on him. And what we're going to do is inside of this guy, we're going to say if this sub I is less than this sub j, and what is he unhappy about here? Oh, it's not, they're nullable. Let's, for sake of this, say that you can't store nulls inside there. And we'll assume that the implementation of this get throws an exception if it walks out the end of the list instead. So if I want to say greater than, if the ith element belongs, actually no, I want to do it the other way. If the ith element belongs before the jth element, then we want to swap them. So what we're going to do is we're going to say this sub I equals this sub j. And I'm going to throw you something here that's going to be super head scratchy, but we'll walk our way through it. The reason I'm going to show you this is that this is actually an idiom that you're going to see in Kotlin. It's not a great idiom because if you're somebody who really isn't familiar with how this works, it's going to look like magic. But I want to show it to you because people do implement swaps this way. Normally, I would implement a swap using something like val temp equals this sub I, and then this sub I equals this dot j, and then this sub j equals temp. So that's normally how I would do a swap. You need this extra little variable to hold on to one of them while you copy over and then use the one you held on to. The magic that we're going to do here, oops, looks like this. And this is where everybody's brain starts breaking. This piece of code here is an idiomatic way in Kotlin to do a swap. I don't recommend writing code like this because a lot of the code that you're going to see in Kotlin is going to be unusual to somebody who's not that familiar with the language to start with. But when they see something like this, they're going to be, whoa, what are you doing here? Now let's walk through and see what this guy is doing. We're going to start with this part right here. The last thing we're going to do is the assignment here. So we're going to just hold off on him for a moment. We're going to start with the this.j also. Now also is one of those scoping functions. He's going to take in the receiver, that's the this sub j, and pass it in as this, and then return it at the end of that. So keep in mind what's going to happen is we're going to pass the this sub j in, hold on to it, do something with it, and then return that value that we had. So that's going to allow us to do the this.j assigned to this.i. His holding on to it is that temporary variable for us. So while he's holding on to that, we're going to say this sub j equals this sub I, and this is going to be the this referring to the list. Kotlin can figure that out based on syntax. It knows that because this is an int, it doesn't have any elements, so it's got to be referring to the outer this. So the this sub j, wait a minute, actually also passes it in as it. So there's no possible conflict. So the it that's coming in here is the this.j. So then while we're holding in onto that this j is it, we're going to say this j equals this I. So we're putting the this I in there. And then we return that value and assign it out here. So it actually does exactly the same thing. It's basically got a little holder for that current value called it. And once we're done with that, we assign it over. So this works just fine. Don't recommend you do it. But I do like to talk about it because you'll likely see it. And I don't want you to think that it's some kind of magic. It really does make sense when you just kind of step through it. Keep in mind, we're going to be calling this function, holding on to this sub j, doing this code, and returning that old this sub j. So it really does the same thing. And it is nice that it does it in a single line like that, but you're likely to blow people's minds away when you do that. So don't recommend you do it. Okay, so here's just a simple little sort, doing a bubble sort here. We're using the natural comparability of integers here at this point. And so this should sort whatever our random access thing is at this point. Not going to go through any of the details on that, but that's basically what it should do. Now, to generify this, there's a few things we're going to have to do. This type here is going to have to be a generic type for the item type. So we're going to put that out here in brackets right after the word fun. I'm going to say item type. And I'm going to replace this with item type, just like that. Now note that this now has a problem because this function says, I don't know what type item type is. So I don't know if it has a compare to. I don't know if I can use that operator. So at this point, you have an error. So we need to provide a little more information here. We need to tell the compiler that item type is comparable. And we can do that by putting a colon after it, just like that, and then pass in that item type to the comparable. So we're going to compare the item type with another item type. Now notice this is perfectly fine now because we filled in that detail to say what type item type is and put a constraint on it. This is actually called an upper bound, meaning that has to be something that extends comparable item type. We have that information. The compiler can now perform this operation because it says, oh, each of those items in that random access thing is an item type. Item type is comparable, and comparable has this compare to function in it. So I can actually run this. And boom. So now we have a much more generic sort here. We're not only doing it just for ints, we can do it for any random access thing, as long as the item type is comparable. Now, if we had a random access with an item type that's not comparable, so let's say that we created a person class and didn't have it extend comparable, we wouldn't be able to use this. This part could be satisfied, but it wouldn't be able to satisfy this part because the items inside the list are not comparable at that point. Okay, any questions so far? Now let's say instead of having the requirement of the items be comparable, maybe we have a random access thing that is going to not only, or a collection, the collections is not only going to provide random access, but the collection is going to provide a comparator so that the collection can tell us how to sort the stuff inside of it. I don't generally recommend you do this. Normally I would say pass a comparator in to your data structure or use an external comparator. But just for this exercise, let's say that the list knows how to do a sort, knows how to compare types of items. So I'm going to come up in here and I'm going to say interface sortable for some type. And what this is going to provide us is a fun compare A type and B type, something kind of like that. And again, it's going to return an int like that. And what we can do is attach this interface to our data structure as well. So if I came down here, maybe I say comma sortable on item type, which now you'll notice that this linked list needs to have that sort function. And I will say probably pass in a comparator. Actually, let's just do that. I'll show you how this might work here. If we actually pass in a comparator to this guy, or we can just pass in a compare function. Let's just do that. So for my linked list, let's put in a parenthesis for a constructor, and we will say comparator, which is going to be a function that takes item type and item type. So we're going to have the two things that we want to know where they are, and he's going to return an int. So we'll just have this nice little function to say how to compare things when we're actually creating instances of it. And what is he? Oh, he's not happy about that there. So let's say if temp, actually we'll do this, if temp value or throw array index out of bounds exception, something kind of like that. Or I can just say out of bounds exception. I think that's more generic. Index out of bounds, that's the Kotlin one. There we go. So that'll let us throw an exception instead of returning that null there. So passing this comparator, and I can now use that in this compare function. I can say return compare. I didn't make that a val, did I? Comparator A comma B. And so now we have a nice generic data structure with this comparator, and the data structure handles the stuff itself. We can actually put items inside of it that aren't comparable. So let's see how that might look implementing it in this function. I'll make a copy of this guy. And this time, I'm not going to care about the item type being comparable. But what I'm going to do is where you say, let's call this sort2. What I'm going to do is say that this random access thing has two constraints on it. He needs to take item type, and he needs to extend the sortable. He needs to be some collection that's going to be random access and sortable. So let's implement that. Let's say we have an item type. I'm going to add in a second generic parameter here called collection. So we have an item type and we have a collection. And if collection just had a single thing to it, well, actually, let's just go ahead and implement this kind of like the first one there. I could say collection is random access item type, kind of like this. And then say collection here. This is kind of a different way to write that first version here. These two functions are equivalent. What this guy is doing is I'm using just a single generic type and then explicitly referencing it over here. What this guy is doing, whoops, I missed my comparable one there. What this guy is doing is defining two generic types, item type and collection, and then just putting this explicit collection as a random access and using collection by itself. I would generally prefer to write this the first way for this particular function, but this is kind of a nice mid route to get to the next thing that we're going to deal with. Notice here that we have one constraint on collection here. It has to be, I never started my Camtasia, so I'm just going to go ahead and use the recording that came from Zoom. This collection here just has a single constraint. It has to be random access of some item type or some subtype of that. Let's create a sort3 that takes things a little further. So this is going to be the one that actually has to be sortable. So we're not going to put that constraint on the item type, but we're going to have to make this collection have two constraints on it. One, it's going to be random access, and one, it's going to be sortable. And there's no way at this location to specify two constraints. So what I'm going to need to do is just say I have an item type in a collection, and this is on collection sort3, but I'm going to need to add a little more information here. We're going to add in an expression here, or a part of the a keyword here called where, to add in some more constraints. So I'm going to say collection, whoops. Collection is random access item type. So that's the first constraint. And then I'm going to say collection is sortable, whoops, for item type. So I've added in 2 constraints there. He has to be random access and he has to be sortable. And you can add any number of constraints that you want on that. Usually you're not going to see more than 2 or 3 when somebody does a where like this. And it's very rare that you're going to see somebody use a where. But if you ever need to put more than 1 constraint on something, this is how you do it. So now we know that collection is a random access guy, so we can do size, we can do get and set. And we know collection is sortable, so that we can do the sort function on him, or you can use that comparator on him. So this is a problem right now because the items aren't specified as comparable. So we're going to have to change the way that looks. So I'm going to say if compare this and that is less than 0. Actually, it's the other way around. It should be greater than is when we want to swap it. If I had tested this, of course, I would have seen that was a problem. So if they're out of order, I want to swap them. So if we're comparing them and they're out of order, we're going to do our swap just like that. This one lets the list itself handle all of the access as well as the actual comparisons for us. Any questions on that? And you're not going to see this too often. But I just like you to know it's there because once in a while, you're going to need to have multiple constraints on something, especially if you get into something that's very complex with regard to generics. Okay, so this is all pretty decent so far, but let's see what happens when we actually try to use these structures in a bigger context. So let me grab my list. Actually, I'm not going to grab this list. I'm going to grab the previous list. We'll go to number 4 here. I'm just going to use the basic list that we have here, doing all this stuff. But what I'd like to do is I'd like to provide a function so we can copy from one list to another. I'm going to call it fun copy. And we'll say we're going to copy from some list. And I'm going to call it, what was this? Did I call it my linked list? Yeah. So my linked list. And let's just start with integers. So this function will only work on linked lists of integers. So I'm going to come in here. I'm going to say I want to walk through all the items in my first list and then do stuff in the second list. And just as a by the way, this implementation of a linked list is not a random access structure. This is actually quite bad because what's going to happen is for every element, we have to walk all the elements before it. You never want to use a linked list for random. I should have thought of that earlier. It's a bad example for that. I should have used an array behind the scenes or something like that. The reason I didn't use an array behind the scenes is because he has generics and I wanted to kind of build something up from scratch here. Never use a linked list for random access. It's horrible for performance. I only use this example. So we didn't have any generics used behind the scenes. Okay, so yeah, that's just a by the way. Never, ever, ever link. That's kind of your main decision point between using a linked list and an array list. An array list is going to give you random access. A linked list is going to give you very fast insert. If you have like an array list, it's going to have to resize that list a lot. A linked list never has to resize. You're just always adding nodes. Okay, so that said, we'll move on from there. So here's our little linked list that we're dealing with here, and I want to provide this copy function. So what I'm going to do is say from dot, we'll go like 0 to from dot size, make it an until. And once again, this is bad because we're going to be walking these items, the first item will get the first item, the second item we have to walk 2 items, third item we have to walk 3 items. Don't worry about that too much. I'm not caring about the implementation here. We're just using it as a logical construct. And we'll do a for each. And then we can say to.insert this sub it. Something kind of like that. Oops, no, from sub it. And what is he not happy with here? Oh, he's nullable in this example. Let's change that back to not be nullable. And we'll say that, or throw index out of bounds exception. There we go. That's better. So here's a nice little copy function. Fairly simple, right? Let's just try this, just see how this is going to work. I'm going to say val list1 equals my linked list. And it's going to be a linked list of int. And let's just go ahead and throw some stuff in here. Insert 5, 4, 3, 2, 1. There we go. And then we'll have a val list2 equals my linked list int. Just create him. And let's do our copy from list1 to list2, something kind of like that. And then see if we can actually print these guys out. So we'll say list2 dot for each. Oh, be nice if I actually implemented an iterator in there. And we'll say println list2 sub it. And let's just see if we get those printed out. We should. There we go, 5, 4, 3, 2, 1. Now notice it's back in reverse order again, because what we did on the first inserts here with the 5, 4, 3, 2, 1, it was inserting at the head of the list on list 1. When we did our copy, it actually ended up inserting them again and re-reversed it. So again, this is not a good implementation of the data structure here, just using it to talk about the generics. So let's say that we want to do this with our animals and things like that. Let me find where I had them defined. Grab these and bring them over to this guy. Put him in there. And let's create a val list3 equals my linked list. I'm going to say mammals. And then we'll do an insert. Let's actually grab the ones that I had from before. Where are they? There they are. So add those guys in there. And what is he not happy about here? Oh, there we go. And let's do the same kind of thing for, what is going on here? Oops. Let's see what this says here. I'm going to float over him. Type mismatch. Required mammal, found dog. Let's take a look at this definition of our linked list. We have a type being passed in, and the insert here says that the value coming in has to be exactly that type, not a subtype. And let's just double check that I'm using the right thing here. So it's mammal. Yep, that all looks good. So somehow we need to specify that you can't only pass in just the exact type, you can pass in a subtype of it as well. In order to do this, we can tweak the type of the parameter up here. Right now it says this is an exact match for a type. But what I can do is put in the word out here. And this will allow us to, oops, actually that's not where I wanted to do it. Nope, that's not right. I did want to put it up here. I can put the word out here, which says that the type coming in to this insert function can be that type or some sub, actually that's an in that I want. Actually, something is not quite right here. because I thought that that would have worked. Oh, the problem was, no, he actually is mammal. Did I have an import? Yes, I do. There, okay, that's right. Okay, I was getting ahead of myself on that because this actually should work. The type coming in, it's actually replacing this with mammal, which means I can throw in a mammal or any subtype of it. We'll get back to what I was talking about in a minute with those other things. The problem I had there is I had a couple imports when I copied the stuff over, and that ended up, dog was implementing this mammal, or the dog was being imported. He was against the other mammal. He was a subclass of the other mammal instead of subclass of this mammal. So now we've got it nice and isolated. I got rid of the rogue imports, and we're okay for now. Not for long, but we're okay for now. So this list here is a list of mammals. We can put any mammal inside of them, and then we can actually print those mammals out. And let's come here and say list3.name, and we'll run them again, and we should see the names printed out just to make sure. Yep, that all looks good. So now the next part. Let's try to use this in a copy function. Let's come in here and say val list4 equals my linked list of mammal. And I'm not going to throw anything into it. I'm going to go ahead and do my copy. Let's copy that from there. So we're going to go from list3 to list4. And notice that our copy is fixed on ints. Okay, well, let's make a copy of that copy for now that works on mammals. Something kind of like that. Thing's kind of interesting here. If I float over this, what does it say? Declaration clash. They have the same JVM signature. That's kind of an odd thing. They look like they have different types, but they actually don't. The generic specifications you have here are really only compile time things. They're not kept in the bytecode. What happens with the Java virtual machine is that these types get erased so that all the information that's left inside the actual compiled code is just that this is a linked list. Now, because of that, these two signatures look exactly the same. It looks like we have from linked list to linked list and from linked list and to linked list, even though they're different generic types. So these two functions have the same signature. They can't both exist in here. So I'm going to have to rename one of them or both of them. I'm going to call this copy 2. And let's look at what's happening. Okay, it looks like that's going to be okay so far. It's going to copy from list 2 to list 3, or list 3 to list 4. And let's just go ahead and print that out just to make sure that those got copied over okay. And there we go. So we have our guys there, and you'll notice that it starts with the second list. Again, it was reversed a second time. And that all's pretty good so far. What happens if we change things up just a little bit? Let's create a new list in here. I'm going to call them list 5. But instead of being of mammal type, let's have them actually be of type cat. Now notice, first of all, if we're trying to insert into a list that takes cats, it has to be things that are cats and anything that's a subclass. So dog does not work here. So I'm going to remove those. And we'll just keep those 3 cats in there, something kind of like that. Now, if I wanted to, I could copy this from a list of cats to another list of cats. But again, I'm going to have to create another copy function for that. So let's figure out how we can fix that first. I'm going to come down here. I'm going to say list 6 is going to be list of cat. And we're going to copy from list 5 to list 6. This is going to be list 6 here and list 6 here. And we're having this issue because there's no copy function that can take a list of cats at this point. So let's see if we can do something about that. Maybe we can make this function a little more generic. I come in here and say copy 3. And instead of specifying the explicit types here, let's make that be a generic parameter to our function. So I'll come in here and say item type. And then put that in each of these spots, saying that I'm going to have the 2 lists of the same type. I don't care what type they are, but they both have to be of the same type. So I'm going to come down here and call copy 3, and boom, that works just fine. And we'll notice that I can also do the same things with those other 2 lists. I can use that exact same function now for all of my copying, which is really nice. We now have a nice generic function taking some parameter and passing that in as arguments. And that's great. Works perfectly fine until you start mixing and matching types. Now you'd think that if we have a list of mammals and a list of cats, that we should be able to copy from the list of cats into the list of mammals, because they're mammals after all, those should hold there. But let's see what happens if we do that. Where's our list of mammals? So our list of mammals is number 3. Let's try to go from our list of cats, which is going to be list 5, let's say, to list 3. And we'll notice here, if we float over this guy, type mismatch, required cat, found mammal. We're saying that this copy function has to have the same item type for both of those lists. Now that's a bit of a problem. We'd really like to be able to put cats inside a mammal list. That should work just fine. And this is a big problem in Java. You can't do it in Java. Fortunately, Kotlin has a way to deal with this. And what we can do, I'm going to go ahead and just copy all this stuff and go to this next package. Something kind of like that. What we can do is set up this function. Let's call this copy 4. And let's get rid of these other copies up here. I'm going to go ahead and get rid of this stuff. And I guess I'll keep those. Whoops. And hopefully we'll be able to get copy 4 to work for us here. So far, it works fine for these other things, right? But in order to go from a list of cats to a mammals, we got to do something a little bit different here. Let's think about this for a minute. What do we care about on this from list? What do we need to do with it? The only things we're doing from it is reading values. And in our to list, the only thing on our to list is that we're writing values. So what we can do is for anything we're reading, that means we're going to output the value. So we take a look at this linked list. Let's see where this is actually being used for reading versus writing. So for this function here, we're passing a value into it. We're basically writing to the list. This operation here, we're taking that value as output. We're producing that information. Typically, you'll see people talk about consuming and producing. So we're consuming the type here. And then here we're producing the type. Let's look at this function here. If I say that on the from side, all I care about is producing those items, if I put an out right there, that's telling us to only use the item type functions, only allow use of the item type functions. They're going to return stuff. And over here, I can say in. That's going to say only allow functions that take item type as a parameter. So we're only using that for insert, whereas we're using this for read. Now, if I accidentally swap those, we'll see that this gives us an error here. So in this, for the out here, because this guy's listed as an in, I can't call the out function. Now in the other one here, this insert isn't giving us an error, but if we float over it, notice that, well, he's not giving us the error. I did expect him to give us an error. Oh, there's the thing there. So we'll notice here when we float over this guy, he's saying that I'm requiring nothing. That's because the to side that says I'm taking something as an output parameter, I can't call anything that actually takes an argument coming in. So it actually replaces the type of those arguments with nothing. Now, nothing is a special case. It's actually a subtype of everything in Kotlin. And there's a few places we use it. Usually, the main one is in something like a to-do call. So where I had something like to do blah, 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 what this ends up doing is this throws an exception. And if we look at the definition of to do, we'll see that his return type is nothing, which is a nice way to describe to you that this function can never return. And in this case, throwing this exception, the function isn't returning. That nothing can then be used as a signal to say, hey, your code flow stops right there. You can't rely on any result coming back. And so you'll see the rest of this function is complaining that it's unreachable code. So in the case of this, it's actually replacing this function with a nothing version of it because we're not allowed to call input functions on that too. Now, if I swap these back to how they should be, we now have the in and out set up right. And let's think about what this means for a minute. So we're going to be reading from this guy. We're getting some value of that type. And we're going to write out some value of that type. So if the lists are both the same type, everything should be fine. Let's think about the case where we're taking a list of cats as our from and a list of mammals as our to. So this is saying that on the list of cats, I'm going to read out cats. And the type of list there, really all we care about here and all we know is that it's a cat or some subtype of a cat. That's what the out tells us. On this side here, we're going to be taking in a list of mammals, which is a super type of cat. And if you think about it, we should be able to read a cat and write it to a mammal just fine. That should work fine. So whenever you say out, it's going to say that the linked list you're passing in is going to be either explicitly that type or a linked list of some subtype of it. Whenever you say in, that means that this linked list coming in here is either going to be of the actual type we care about or some super type so that we can actually place things into it. If we write this, now we'll see that all of these functions work just fine. And that's kind of interesting. This is called call site variance. We're providing some ways to replace the actual types of these guys with super types and subtypes. And by limiting them to outs and ins, we can be comfortable, and the compiler more particularly can be comfortable, that what we're doing with them makes sense because we're going to be reading cats and writing mammals. Now let's think about if we did it the other way around. If we had a mammal coming in here, so we're saying that item type is going to have to be a superclass of the mammal. And item type here is going to be a subclass of cats. Now, we look at those two constraints, and there's just no way for that to work. You can't pass in that way because it's not possible for something to be a subtype. It's not possible for, in this case, mammals to be a subtype of something and cats to be a supertype of something, of that same something. So if we came down here and reversed this, this should give us an error saying it can't meet that constraint. So if we look on here, it's going to say required a cat, found a mammal. And that's not going to work. It's like, because this guy up here ended up setting that when it looked at the, where is he? When it looked at this guy here, it says, okay, the item type should be cat. Well, we're passing in a cat. So it's going to be cat or some subtype of cat that we're concerned with. It can't end up doing the super type over here. So these constraints on here make sure that you can only pass in some valid data. So let me undo that list of mammals to a list of cats, which shouldn't work. I mean, thinking about that, you can't just take any old mammal and put it into a list of cats. If you happen to get lucky and all the mammals were cats, that might work, but there's no way for the compiler to know that. The compiler's going to look at it and say, well, you could have platypi in there. And I don't want platypi in my list of cats. It just won't work unless there's something I didn't know about the relationship between platypi and cats. You know, maybe a platypi is a subclass of cat. So this function here allows us to specify changes, the variance in this. Now, this guy here is called covariant. Covariance, and in defines something called contravariance. I'm not going to ask you questions about this on the exam, so don't worry about it. I forget about which is which sometimes here and there too, so no big deal. But just if you ever see the words covariance and contravariance, that's what we're talking about here. Something that has an out parameter, it's covariant. If it has an in parameter, it's contravariant. And there's two things this does. One is allow this type to be super types and subtypes. So we can actually have a, in the first case where you have a list of mammals to mammals, this can be a mammal or any subtype of mammals. And over here, this could be a mammal or any super type of mammals. And that would have been just fine. The other thing it does is it also restricts which functions are going to be callable inside here. So if you really wanted to control the behavior of what's being used in an in context and an out context, you can put those on there as well. So maybe you have a function that's going to consume things, and that's all you care about. That would be ending up having an in parameter on there, which would say you can consume it. So the call site variance gives you a lot of flexibility here when you're actually using a data structure. We can also use declaration site variance. Let's create a, let's see. Let's take a look at these guys for a second. I'm going to go ahead and copy this example over to number 6. Something like that. Let's think about what these guys are doing. Notice how this guy, we're only using type as an in parameter. By defining this as an in up here, it's locking us down in this interface to what we can do with it. So we couldn't accidentally use it in an out context. But then it also gives you that ability that if you have a comparable of some type, you can actually relate it to a comparable of a supertype or subtype. So if we take a look at this guy. Let's go down to our main. Did I have a main? I didn't have a main. Let's put a main down in here somewhere. So down here, I could say val x equals comparable, and I want that one there. And I'll just pass in a string. Whoops, I want to say object comparable. And I'm going to say return compared to others. So I'm just going to cheat and use the actual implementation they have on string behind the scenes. So this is x is a comparable. Actually, no, I want to do this on the animals. Let's do it on number 2 rather than copying them over. And we're going to say name compared to other.name. Wait a second. I meant comparator is what I wanted to work with on here. Yeah, comparable is going to help me there because I don't have that. So let's make a copy of this guy and call him comparator. And we'll say compare. He's not going to be the operator version anymore. We'll say a type. be type, something kind of like that, and make that in. This guy's not going to have the in. And so if this is comparator, and what is he unhappy about? Oh, let's re-implement that. And there we go. And then we can say return a.name compared to b.name. So there's a nice little comparator for a mammal. Let's say that we also had a comparator for a cat. And we'll just implement them the same way there. Now, these are two very different types there. If I start off with this comparator not having in and came along here and said val z colon comparator, this is what I get for using the same name as in the real library. If I actually define z of type comparator mammal, I can assign that to x. And that's perfectly fine. But if I try to say z equals y, it's going to yell at me. If I float over him, he's going to say, I'm expecting a comparator mammal. That's a comparator cat. All I want is an explicit match there. So if I set this guy up to be in, let's see if that'll work. And we'll see that no, in that case, he's expecting him to be some super type of mammal. So if I switch this around, boom. In this case, Z, it's a comparator cat. That's exactly a comparator cat, so that works. In this one, he's a super type, so I can use him. And if we think about him again, when we're trying to sort these two guys, we care that, let's see, how do I want to word this? We need a comparator for a cat. Be that or the super type. So wait a second. Why does this not seem to? I'm having one of those moments where it's not making a whole lot of sense to me. This one. So we have a mammal. Oh, okay. I got myself wrapped around an axle there. So what we're saying here is that I can pass in a cat comparator. And what other type of comparators can I pass in successfully here? It's not like we're trying to pass a mammal to the comparator for a cat. We're saying that I need a comparator that is going to be able to take, oh, wait a minute. I had a good way to explain it and I lost it again. It'll come back to me. Give me a second here. I'm gonna have to come back to this with an explanation after the break because I'm blanking on a good way to explain this one. I just had it for a moment and then it went away. I don't use this all that often. So, this particular type of syntax. So I'm gonna have to think about that and come up with the right way to say it. I almost had it and then I lost it right at the last second. So I apologize. So revisit. Those are my initials, by the way. So I'm going to come back and look at that one again momentarily. So we'll see if we can come up with a good way to describe what's going on there and why that actually is something we care about. Okay, so we can also do something similar with things that produce things. So if there's a like this guy, this random access, we're only using these guys. Well, no, he's using them as an input. If we just talked about the getter side of it, We could talk about it using an out parameter. If we talked about the setter side, we could talk about it using an in parameter. It's coming in here. And if all we cared about was getting things, if all we cared about were setting things, then we can use different versions of this random access that are either superclasses or subclasses, depending on what we're trying to get into. Don't use these all that often. Most of the time I'm using them as call site variants, which makes a little more sense, but I'll come up with a good example for that during the break. Okay, so any questions other than that nonsense? Okay, so let me see. The next thing I wanted to talk about, where was he? Just looking for the example that I wrote up. That's what I wanted. Okay, good. So this next one is a little different than these other ones. Let's say that what we want to do is we got a bunch of data. Maybe there's all these different animals, and we want to have a different type of processing that we do for each of these ones. And we want to make that processing more dynamic. We want to set it up so you can register a processor. Think of a system like Android, where you can actually install new applications and they add things to the system, like new ways to display HTML. You can install a new browser, for example, new ways to edit images, new ways to, make a phone call. You could have different phone call apps. We could have a system where we have some plugins that provide new types of processors for data to make our system more flexible. So kind of as a starter on this, let's think about having some way to register processors. It's going to be a map from the type of an object to a processor for that object. So let's say that I had val processors equals mutable map of, and I'm going to have a K class, which is the Kotlin class, and a processor that can take anything and do something with it. So now, first of all, this guy here, this is what's known as a wildcard. And if you don't care specifically about using that piece of data, so if you're, in the case of the ins and outs, you're limiting things to just using functions that can take it as an input, something that you can take functions as an output. If instead of that, all you care about is either just what the class is, which is in this case we're doing, or other functions. So let's say that you were dealing with a list that had a size. Size doesn't matter based on the item type. If the only thing you cared about was what's the size of a list, we could say star when we're using a list coming in. So if I had something like some function and I have a val list equals my linked list, I'll just use that. Oops. Let's use that one there. And let's say we had another function here, print size. We could take a list that's a my linked list and say, it can be a linked list of anything. I really don't care. All I care about is the size. And so I could print out list.size, and that'll work just fine. And I won't be able to use any of the other functions for that actually care about the type, but I can print out that size. Now there's a little bit more to it. I don't want to really get into the stars too much. There is a case where it becomes an upper bound, whatever the actual type is. I'm not going to worry about that right now. That's something that most of the time you're just going to be using it like this, saying, I simply just don't care. And so you could use it like that. So what we're doing here is we're just saying, all I care about this class here is basically a key in this map. I care what class it is. I don't care to ask any questions about it. So I'm going to say it's a K class. Now this map that I'm going to create is going to say for a given class, I can have one processor registered for it. And that processor is going to take some value and produce some data based on it. So I need some way to register these things. I'm going to say register one K class, or let's say class. Oh, I can't do that. Let's say K class, and I'll put a star there. and I'll say processor, any unit. And then this is going to just say processors sub K class equals processor. Boom. So we're registering that. And if we wanted to actually use it, I could say process some object. And then what I can do is look that guy up in the processors map. So I say processors sub value dot value : class. That's going to get the K class. Invoke, passing in the value, something kind of like that. And that could work. So this is going to try to look up a processor, and if one exists, run against it. And you might want to also have something like throw illegal state exception, no processor registered for type $value : class dot simple name, something like that. So this would give us the capability to process some data very dynamically. Anybody could register something, and then anybody can process it. And I've used patterns like this quite a bit in some of the code that I've written. I had some user interface frameworks that I wrote up that there's different modules can contribute new UE components. And the UE components would have processors behind them to do some interesting things. And because these different modules may or may not be included in your application that you're building, this dynamic registration was necessary and worked very well. But there's some problems with what I've written here. Let's think about what this registration looks like. So I could say register string : class, and then some processor here. And right now, notice that the parameter coming in is an any. But what if I said n : int and then tried to do something with it? Actually, is that going to work even? I actually want to make that be an in any. That's actually not what I want to do. We'll come back to that in a second because I got to do it in the generic. But right now you'll notice that this is an any, which doesn't really help me because now I'm going to have to cast the thing to a string. So I'm going to have to say it as string and then do something with it there, like maybe print the length out or something like that. So this might be a registration thing. I might say, if a string is processed, then go ahead and print the string. So in this case, I should get a 5 printed out. Let's just see if that works. Whoops. Code from other places is going to give me grief here. There we go. So we got our 5 printed out. That was just fine. And that can be pretty useful, but I'd like to be able to have this know what actual type is coming in here. And further, I'd like to make sure that this guy and this guy are actually acting on the same type. So what I'm going to do is let's call register2. We're going to make him generic. I'm going to put a T in here for the type. And I put that T in both spaces here. Now notice that K class isn't very happy about that. The argument is not within its bounds. It's expecting the upper bound to be any. Right now, the default is any question mark. It could be anything nullable or not. We want to say this thing can't be nullable. So I'm going to say it extends any. And that's going to make the K class happy because he has to represent a class that exists. He can't represent a class that doesn't exist. And now what I've done is associated this K class with that processor. Boom. And that's kind of nice there. That actually seems to set things up just fine. They have to both be the same type. But now I got a problem here. Required any, found T. So the, what was I thinking of on this one? Actually that, any unit found T unit. The T is a subtype of any. And this one's explicitly an any. I couldn't do that. That didn't work. I'm trying to remember how I fixed this. That works. I mean, if I did this, it's kind of gross. That'll work if I explicitly cast it. But I thought I had this working differently. Huh. I thought I had that working a different way, but actually I didn't. So this, actually we're gonna have to cast it, unfortunately, at this point. This is actually one of the issues I've had with writing these up in the past, is when I'm using these wildcard type situations. Sometimes you have to cast in and cast out, but you wanna try to hide that in this function. By doing that now, if I call register 2, notice that the parameter changes to a string. So now I've made it easier for the user to use things at the expense of it being a little bit harder for me to do things here. And I thought I had a way to trick around that, but apparently not. If instead we wrap this processor as a class, so if it's not actually just a lambda we're storing in here, then we can actually have that be covariant. So if I did something kind of like interface processor, I think this is what I've done in the past, because I originally started with a Java framework before I moved into Kotlin here. And yeah, I'm pretty sure this is what I did with it before. So I can have a T : any in there. And then this guy is going to have a fun process value T. And then if I had a processors 2, I could have this be a processor star as well. And then I think this would actually work. I said processors 2. Oh, but he needs to be a processor. So let's change this back to processors and then do this. 3. And we'll leave that as that one, but this register 2 will do that and change this to be a processor T. And then that'll work. So this function here now links the type here and the type there. And if I try using that, that'll work. Now, what did I just do up here? I just declared this as a functional interface, which means I can actually use it as a lambda, as opposed, because if there's only a single, if there's a single abstract method inside of it, you can declare it a functional interface and use it as a lambda, which allows me to still use this same syntax, keeps things nicer. So now we have that register, and if I look at register 3, same type of thing. Yeah, that's what I've done in the past. I made this functional interface. So this will allow me to keep track of these guys, saying I have some class and some processor. Notice there's no relation between them here. There's no way to do that, unfortunately. I wish you could say that each pair has to have a relation, but there's no way to do that. This function is doing that for you. If this is the only function that exposes this guy, so we made these guys private, and so they're only accessible inside this file, then we're protecting it and saying the only way you can add them is if the two are actually matched. And then when we store them, they get kind of generified again. When we process it, then we can pick it up and use it. And so I can come into here and say process 2 is going to be processors 2. Notice that it's not going to be invoke anymore. It's going to be process, passing in the value. And now with this guy, when we get him back, notice how it says required nothing. The problem here is that we have a star here. So he doesn't know what to do with that. He can't actually process it. So we're going to have to cast it as well. So we'll take this guy and say as question mark processor T. Actually, this should be value T coming in here with a T over there. And T colon any. There. And so now both of those are okay. We'll set up our cast. And oops. Oh, I don't think I needed the parens. See if I can get my parens in the right place here. Come on, fingers. There we go. That's what I want. So we still also needed the same kind of cast on the, in this case, on the output instead of on the input. But one way or another, you're going to need to. It depends on what this guy actually is how you're specifying it. In this case, I made it easier for my input, but harder on my output because I have to do that cast, unfortunately. So if I try doing this in either case, I can say process Scott or process to Scott. I should get 5 in both cases. There we go. So this pattern that you're going to see using some kind of map of processors or other type of thing you could do with some data, and this registration, you're probably going to come across that at least once in your life, where somebody's setting up a framework and you have to have some way to say, I want to dynamically decide how to do things. This can let you do that. I'm lazy. I don't like to re-specify things here. Let's take a look at what we got here. This register function, I'm actually saying string here, but the lambda also has a string in it. So is there any way I can get rid of that? I can like whittle that down to just being able to specify just the lambda perhaps, or just a processor class perhaps. There actually is this thing in Kotlin called a reified type. And what I can do, I'm going to call this process 3. Whoops, not process. I want to come up here to the register. That's what I wanted. So for this register, let's make a register 4. Let's say that I don't want to explicitly pass the class in here. Notice that the type here is part of that lambda or part of that processor type there. So actually, let me make this be a type processor. I'm going to copy register 2. Call it register 2A. I'm going to get rid of this class here. My processor has the type in it. So I should be able to somehow say, based on that type, let me do something with it. And you can't do this in Java, but what you can do in Kotlin is put here T : class, which right now won't work because the type gets erased. But if we throw the word reified in there and make this an inline function, what this ends up doing by being an inline function, it takes whatever this type was here and actually replaces the type name there in line. Because we're doing an inline replacement of code, it can do that. And so the real type is going to be used there exactly how we want it to be. And what is he not happy about here? Public API function cannot access non-public, private, blah, 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 blah. So a couple little things about this. Whenever you say inline function, it has to be something that's going to be accessible to whoever's going to call it. He's going to be a public function, and this code is just going to be replaced as is. Because the code is going to be replaced as is, we can't reference variables that aren't accessible to the call site. So we have to do a couple little things here. We're going to use the reified function here just to understand what that T is and make this just call the other one. Register 2, passing in T : class and the processor. So we're just using it as a shorthand. And what this is going to look like when we actually call it is I can say register 2A, not specify that, and maybe say S : string here. Boom. And what this is doing is because I put the type in that lambda, and now it's directly in there, this register function can figure out the type based on that, and then pass that in as the string : class for me. So it's a little extra shorthand on there. There's another thing we can do on this. We can explicitly specify the type. So if instead of writing it like that, I said register to a string, I can now use the it syntax again. And by doing this, I'm explicitly passing in the type that I want to use inside the function. And that gets passed along as t to the lambda in this definition here for the processor. And boom, I now have a syntax that I actually like quite a bit more, because I don't have to have that : class. I don't have to have an extra parameter floating around in there. I think it just reads better. And there's going to be other times when you can have functions like this where, maybe it would look more like a register to a string blup blup. So maybe there's something without any other parameter other than the reified type. And sometimes that can make your code a lot more reusable. One place where this actually is used is in Android. There's a function called find view by ID. And he's going to take in an ID, which is an integer, and he's going to return some type. I'll say view. And that's going to be reified. Actually, I don't even know if this one needs to be a reified type. Okay, let me actually try that out real quick. I don't think I need to reify that one. I think it'll work just fine like this. Yeah. So when I use this one in Android, normally you'd say find view by ID, whatever the ID is, as whatever view type you have. So you might see code that looks like that, but because of the syntax in Kotlin, I can say this, which I think reads a little bit better there. Something kind of like that. So this actually prevents you from having to cast by having that syntax, but no, I didn't need to make it reified. So that, for some reason I was thinking that needed to be reified, but nope. But this syntax, I do tend to like this syntax a little better. It explicitly defines that for you. You don't have to put the type for the parameter in the lambda there. Okay, any questions on that? I know I've thrown a lot at you in the last hour and a half. The main things that you're going to want to know, I may ask you what reified means, just kind of at a high level. And it's basically going to be using the type that's passed in directly. So you can actually get its value, get the value of the type. That's the only way to actually get that value instance of the type when you have it as a generic. Otherwise, in functions like this, there's no way inside of this to say, what is that type? What can I do with it? But mostly what you're going to need to know is the first couple that we did in here, where we're talking about the idea of passing in types, telling, binding the type to so it has an upper bound, and doing something like, I'm not going to have you do any one of these. That ends up getting a little more complex, but I may have you do some that define a second type dependent on the first type, kind of like we did up here. So understanding how those work are really the important parts there. Okay, any questions on that? Okay, and my lights are starting to flicker again a little bit here, so I'm a little worried that I'm going to lose. So what I want to do, I really pretty much covered what I wanted to cover for today, with the exception of figuring out that example. So what I'm going to do is I'm going to call the class now, and I will work on the setting up an assignment here for this. And I will fix up that example that I wanted to show on the in and out and post that as an announcement. Are there any questions? Cool, cool. Well, have yourselves a wonderful night, and I will see you guys next week.